Is there anyone here who's never seen Star Wars? There's always one or two. Never fear, I'm not going to assume too much Star Wars knowledge in your ears. There was a time, of course, when this great cultural phenomenon was relatively unknown, and I'm old enough to remember that time fairly vividly. So I remember as a very excited 10-year-old being taken along to see Star Wars in the summer of 1978, and it did have a big impression on me. So all these years later, as Professor of Astrophysics, I've never been too ashamed of my Star Wars past, and in fact you'd only have to take a look at my office and see all the Star Wars models and so on are still there. But it's very much the Star Wars present. And in a way, as Nye mentioned, I've tried in doing science outreach to harness, wherever appropriate, science fiction as well. It's been such a huge influence on our popular culture for the last few decades, in a way that it's easy to just overlook, to forget that there was a time when it was much more of a niche market in television and in films, whereas now it's just huge, and it's a way to reach out to people and tell them a bit about science that perhaps when I was a student myself a few decades ago, it was a bit harder to make that connection with popular culture. So what I'm really going to talk about tonight is partly the physics of Star Wars, but also a little bit along the way the experiences I've had of using this topic, the physics of Star Wars, as a tool for doing engagement. And the project that Nye mentioned, that was the title of my fellowship for the STFC, not Swindon Town Football Club, but the Science Technology Facilities Council, duly acknowledged on my slide here. They funded a third of me for the period from 2010 through to 2012 to lead a project that focused on not just schools outreach, but also outreach to the general public, both within the UK and indeed beyond. And I'll tell you a little bit about that as we go along. But I called the project Exploring the Dark Side of the Universe because it was very unashamedly trying to connect the cutting-edge astrophysics that STFC supports to some of the more weird and wonderful ideas that one meets in the world of science fiction. And I suppose the key message I was trying to get over is the same message I would hope you would leave with tonight, is the realization, if you weren't already aware of this, that the real universe we live in is, if anything, stranger than whatever George Lucas dreamed up. So that's really what I want to cover tonight. And I guess I should maybe just say a little bit more about the kinds of things I've worked on in my research to sort of kick things off. And back when I was a graduate student and a postdoc, I guess we were still coming to terms with the huge expansion and explosion in information that we had in the field of cosmology. Cosmology is the study of the universe as a whole, not concerned so much with the properties of this particular star or that particular planet, but trying to get the big picture of what the universe has been doing, what it might do in the future. And absolutely key for me was the launch of the Hubble Space Telescope in 1990. It provided a whole wealth of data about nearby and far away galaxies and stars that allowed us to answer a number, or at least try to answer a number of really important questions that for generations before had not been properly addressed. And real basic stuff like how old the universe is and how big the universe is and whether the universe might continue to be around forever. Some of those questions we're still grappling with 2 decades later, and that's very much what my outreach fellowship project was about, was conveying the excitement of some of those big ideas that STFC is grappling with and trying to link some of the really weird and you might say extreme astrophysical concepts that you have to take on board when you're studying the universe as a whole, to try to draw parallels where appropriate, or perhaps contrast those ideas with what you encounter in the world of sci-fi. So the Hubble Space Telescope's back in the news because tomorrow the movie Gravity is about to hit our screens, and I was travelling overseas a few weeks ago and I resisted the temptation to go see it. I was in Malaysia, it was already being screened over there, because I thought I'll wait until I'm back in the UK, go and see it with the family, and I'm looking forward to seeing that very much, although I understand that they've got some of the signs a wee bit wrong in Gravity, not least, not so much a science point, but just in terms of the chronology of space travel and so on. Of course, the space shuttle program is no more, and that means that the Hubble telescope that's been up there for 23 years now, well, it's kind of reaching its final stages because there isn't any immediate plans to do any further refurbishment and servicing of the Hubble telescope. But for the purposes of the Gravity movie, which I imagine many here will want to go see as well, and then you've got your space shuttle and the Hubble telescope back there again. So over the 23 years that Hubble has been up there, there's been various servicing missions that have allowed us to fit new instrumentation onto Hubble and allow us to peer ever deeper into the universe. And about 10 years ago, there was an image taken by the Hubble telescope called the Hubble Ultra Deep Field that was even deeper than the previous Hubble Deep Field in the mid-90s. And one of the very faint specks of red that you can probably barely make out at all in this wonderful image is shown here. And that, in 2010, was imaged by some ground-based telescopes, which are even bigger than Hubble, although they have the disadvantage of having to look through our atmosphere, which annoyingly doesn't stay still, and therefore it means that even with a very, very big telescope, sometimes your ability to see faraway things is not quite as good as the Hubble Space Telescope. But what you can do is you can do what we call spectroscopy. You can study the light, you can study the colours of the light, and you can deduce something about very faraway things. You can deduce that they have what we call a redshift. Again, a term you've probably heard before, which is to do with, we now understand, nearly 100 years after it was sort of first observed by Edwin Hubble, after whom the telescope is named, we now understand that redshift is to do with the expansion of the universe. And the observations taken by these giant telescopes in Chile, following up on the image, the photometric image of this little red speck that had been caught by the Hubble telescope in the ultra-deep field, revealed it to be somewhere in the region of about 11 or 12 billion light years away. So I guess this basically illustrates that while a lot of the science in Star Wars maybe isn't quite on the money, as we will see as my talk goes on, at the very least George Lucas got the bit at the beginning correct. And again, if you picture me as that very excited 10-year-old watching the movie in 1978, it really is quite a profound thing and a hugely gratifying thing, despite all those committee meetings that I refer to think I'm doing a job where I get to do what George Lucas was capturing in that first moment on the cinema screen. So I'm studying galaxies, the light from which set out a long time ago from far, far away. So the Star Wars universe has been the backdrop to my professional life and indeed my life through secondary school as well. And it's never been very far away. Indeed, with the advent of DVDs and all of that, I now have a 9-year-old daughter who I was able to inculcate into the Star Wars universe. Rather sadly, she's moved on to Harry Potter now. There was a phase where she could name all the characters and name all the planets, and I don't know whether my wife was more proud or scared, but nonetheless, it's a great testament to the movies that they do seem to have this power to reach out to new generations of Star Wars fans. Now, whether that will see through to 2015 and beyond, with Disney taking over the franchise, but I, for one, am quite excited about Star Wars Episode 7, all the more so because it appears as if the director is going to be J.J. Abrams. And I should say that I'm going to be quite even-handed tonight. I'm going to make a few references to Star Trek as well, because I've never bought into these arguments about, you know, you've got to be a Star Wars fan or a Star Trek fan. I really don't see why you can't be both. And indeed, hopefully J.J. Abrams will help to unify the two groups. I was quite excited to notice a few days ago that they're actually advertising now for actors to appear in Episode 7. And then I was a bit depressed when I read the age profile of the actors they're looking for. They're looking for a girl in her late teens. Well, okay, I wouldn't have qualified for that anyhow, but they're looking for a strong and single-minded male character in their late 20s. So sadly, my ship has sailed in that one, but it does again indicate the ongoing power of Star Wars, that when we got news of this, you know, we basically put it on our internal email around our undergraduate classes, and it's been the talk of the steamy, as we say in Glasgow, for the last few days I've been picking up in the common room that they're all speculating as to who might go along to the auditions. It reminds me of actually what happened a few years ago when they were filming World War Z, or World War Z as I rather obstinately continue to call it. They were filming that in Glasgow, and they were looking for lots of zombie extras, and of course the joke was, well, how could you really tell the difference between the student undergraduates and the zombie extras? Exactly how they'll dress them up for Star Wars isn't clear, but again, you know, it's out there. It's part of what everybody's talking about right now, and I very much look forward to see whether our three protagonists will indeed will appear in episode 7 in a year or two. So that's just sort of just general background. Specifically, what am I going to talk about? Well, when I've taken this as a theme to do schools outreach, of course you want to emphasise how fun Star Wars has been for me, and hopefully that will be the case also for school kids that you talk to. But there is, still, I think, a desire to get some proper physics in there. And frankly, a talk on the physics of Star Wars could be extremely short. You could say, well, there isn't very much because they get it all wrong. But I'm trying to approach it in a slightly more constructive spirit, which is to say that if we take, for example, these three broad themes of spaceships, weapons, and planets and star systems, even though we know that a lot of it is just plain nonsense for the purposes of conveying an exciting movie in 2 hours, if you wanted to make it realistic, the time it would take to travel from one planet to another, then the movie would last for 50,000 years. That wouldn't really work. So obviously there's a lot of poetic license has to be taken. I've tried to use this theme as a way to just look at some of the extreme ideas in physics and astrophysics and just speculate a little and think, well, if there is possibly any truth in what you see up there on the silver screen, then what areas of physics might give us some hints towards what those truths might be. So that's what I'm going to try and do tonight. And I'm going to sprinkle it with some liberal quotations. And if I get any of them wrong, please correct me. Although I don't think I will, because in fact I have a reputation back at Glasgow of being, the ultimate Star Wars guru. In fact, over the years I've occasionally had emails from some of my students where they put quotations at the end of their email. And not only don't I mind, but I also correct them when they get them wrong. So, basically the students regard me as the local expert, so I will do my best to live up to that reputation and get the quotes right. You might recognise this one. It's just before Han Solo and Chewbacca launched themselves off from Mos Eisley Spaceport in the general direction of Alderaan, only to discover that it isn't there. Apologies to the people who haven't seen Star Wars yet. But I just want to focus on this idea of hyperspace travel and what, if anything, there might be in real physics that could give us some clues as to how hyperspace travel might happen. Well, if it's got anything to do with real physics, it's probably got something to do with this chap, because Einstein's theory of gravity, which of course underpins a great deal of the research I do in cosmology and in gravitational waves, does maybe give you some wriggle room to allow for some rather unusual and extreme modes of travel in the future. So let me say a little bit about that. So I guess everybody here will know lots about Einstein already. It's interesting that even more than 60 years after he died, he's still generally regarded as one of the most famous scientists of all time. In fact, there's various polls that have been done in the US where they ask them to name a living scientist, and quite often Einstein gets I mean, I have seen a National Enquirer cover that refers to Einstein's brain being kept in a jar somewhere. But as far as I know, he did pass away in the 50s, but nonetheless his legacy lives on. And in fact, in 1999, Time magazine voted him Person of the Century. Not Scientist of the Century, but Person of the Century. Actually, that was the editorial board decision. They did have a public vote, and the public voted for Elvis Presley. But Einstein, hugely influential figure in science. I have an Einstein action figure. I should maybe have brought it along to so what does Einstein's theories have to say about hyperspace travel, if anything? Well, it's all to do with Einstein's theory of relativity, which he formulated and published in his miraculous year, 1905, when he published groundbreaking papers in several different areas of physics. But his work in relativity, well, and again, I'm sure you've a good grasp, many of you already, of roughly what this is all about. It's to do with the equivalence of space and time, the fact that there isn't this rigid framework of absolute space and time that everyone will agree on. It really depends on how you're moving relative to other observers, hence the name relativity. One of the consequences of, or one of the embedded principles of relativity is that nothing can travel faster than the speed of light. So that wouldn't seem to be very encouraging if you're looking for a mechanism for travelling through hyperspace, but let's leave that sort of minor issue aside for the moment and just think about how else one might exploit some of the ideas of relativity and link them to what goes on in the Star Wars universe. So among the consequences of Einstein's special theory of relativity was the equivalence of matter and energy, which we get in this famous E=mc² equation. Every second the sun converts 600 million tons of hydrogen into 596 million tons of helium, and the missing 4 million tons gets converted into energy, and that's what powers the sun for a very, very long time. So this relativity, this relationship between distances and spatial measurements and time, and how that depends on your point of view, your frame of reference, well, again, you know, that's just sort of captured in a neat little phrase. You can't tell if you're moving. So we all have a perception as we sit in this lecture room that we're not moving. But on the other hand, the Earth is turning, the Earth is orbiting the Sun is orbiting the centre of our galaxy. So actually, you know, we are moving along at a fair old lick. And even within the context of just special relativity, which is supposed to just be concerned with the easy stuff, where you're moving at a constant speed, constant velocity, maybe again we can just draw upon our everyday experiences of situations where sometimes you can be a little bit fooled. And one such example is on the Glasgow Underground, which is a rather small and perfectly formed underground. It's only one line, so it doesn't really matter if you go the wrong way, because you'll still get there in the end. It's like the Circle Line in London, only smaller. And it's known as the Clockwork Orange, because all the trains are orange. And one day, early this year, I went off and did a bit of filming on the underground and managed to avoid the attention of the security guards. But this is so several of the stations in the underground have a single platform in the middle, and sometimes you'll have two trains passing each other, one going one way, one going the other. And the point of the little video is to just, you know, maybe remind us. I'm sure you can think of other situations on board a train where for a second or two you're not very sure whether it's you that's moving or maybe the train you can see outside your window that's moving. Now, of course, if you have some fixed external reference point, like a no smoking sign on the opposite wall, then you can tell that it's really you that's stationary and the other train that's moving, but sometimes it's a bit hard to tell. And that was really one of the key ideas of Einstein's relativity. And consequently, again, even in Einstein's day, there would be situations where you could sort of do this way of thinking. You could think about either you're the one that's moving or it's someone else that's moving. And there's a story about Einstein going to a conference in Oxford, and the conductor was coming up to take his ticket, and he said to the conductor, "What time does Oxford reach this train?" The conductor thought he was going to write one here. And in a sense, he has a point, because from the point of view of you sitting on board the train, you can just about convince yourself that it's Oxford that's rushing towards you. So does that have any bearing on a possible connection to Star Wars? Well, if it were to, then one might imagine Han Solo saying to Chewie, as they're about to blast off from Mos Eisley, "What time does Alderaan reach the Millennium Falcon?" So that scene that I showed before with the clip travelling through hyperspace like Dustin Crop's boy, that's just before they're about to launch. Again, a few movies later, Return of the Jedi, because the special effects budget had got a bit greater, there's a scene where you see a whole bunch of spacecraft about to take off into hyperspace, as they call it. So let's watch that one just for a bit of variety. This is Lando Calrissian. Basically, it's there for dramatic effect and little else, but if one did want to try to look for some kind of scientific framework for this, it kind of looks as if the stars are stretching towards the spacecraft, and of course from their point of view, just like Einstein sitting in his train and seeing Oxford rushing towards, and maybe relativity provides us with a framework for thinking about it that way. In particular, as I said earlier, I want to emphasise that this is not a solely Star Wars view of hyperspace travel, because in Star Trek as well, most recently the J.J. Abrams reimagining, there's a neat phrase where Simon Pegg, aka Scotty, Montgomery Scott, says, "Imagine that, it never occurred to me to think of space as a thing that was moving." And there's a nice little quote which I can never remember right, so I've just put it in to make sure I get it right. He talks about the notion of transport beaming is like trying to hit a bullet with a smaller bullet whilst wearing a blindfold riding a horse. And so with those kind of difficulties, you wonder, how they can ever get from A to B successfully. So, if that sort of basic idea that somehow you're stretching space in order to take a shortcut through hyperspace, how could you do that? Is there any plausible way in which you could stretch space? Well, that is where, like I said at the beginning, it becomes almost that the real universe is weirder than what science fiction dreams up. Because precisely what Einstein has told us is that space-time is a stretchable, malleable thing. So here's me sitting in Einstein's lab in Washington. This is a statue at the National Academy of Sciences. So the thing that he actually got the Nobel Prize for is the middle equation. You can probably barely read the details anyway. And that's to do with the physics of really how this laser pointer works, what we call the photoelectric effect. We've already had E equals mc squared, the famous equation, that's special relativity. But where all of this stretching and bending of space comes in is his so-called general theory of relativity, which he published in 2015, Freudian slip, 1915, 1960. We're approaching the 100th anniversary of that, and again, I'm hoping to take part in lots of public outreach to publicise that. So what's general relativity all about? Well, just as you can sum up special relativity by a neat little phrase, you can't tell if you're moving, for general relativity, the equivalent would be something like this. Again, many of you will have heard this before. Space tells matter how to move, and matter tells space how to curve. Or more correctly, space-time, because you have to think of space and time together. This isn't a phrase that's due to Einstein himself, it's due to John Wheeler, famous physicist that was working in this area sometime after Einstein had originally proposed the theory. And there's little stories about, in the initial years, after Einstein had published the theory, that like hardly anybody understood general relativity. There's a famous story about Arthur Eddington being asked, after he had experimentally verified Einstein's results, that he must be very proud to be, the third person to understand general relativity, and Eddington was rather hesitant in replying. And the journalist said, "Well, come on, Eddington, don't be so modest." And he said, "On the contrary, I'm trying to think who the third person is." So, one of the legacies of Einstein's work is that these days, nearly 100 years later, we do teach this stuff as part of undergraduate or postgraduate degree programs, and it's pretty challenging stuff. But the key ideas, the key physics ideas, without any of the complicating mathematics, are really best summed up with this picture of a stretched sheet of rubber into which you drop a heavy object, and that will cause the rubber to deform, to bend. And this actually is something that we try to use in a lot of public outreach. This is our, as we call it, our rubber universe, which we would take to science centres and museums and so on. And the kids just love trying to roll coins around to make them go in an orbit around the mass in the middle. And that's analogous to how you would think of a planet orbiting a star or a moon orbiting a planet, that it's not feeling a mysterious force from afar, it's just experiencing the local bending of space and time. And a consequence of all of that is that if you think of the rubber sheet as moving, as it would if you first of all drop a heavy thing in, the heavy object is going to bounce and the rubber sheet's going to wobble, well, those wobbles are what we call gravitational waves. So again, we're in territory where the science actually seems weirder than the science fiction. But gravitational waves the shaking, the wobbling of space and time due to violent cosmic events, that's really what we are seeking to detect in a worldwide collaboration, which I'll say more about towards the end of this time, or indeed I'll be happy to chat to people afterwards if they want to hear more about that. Detecting gravitational waves, just let me say a very brief word about it now, is, again, sounds more like science fiction than science, but it's using giant, what we call laser interferometers, where the arms of the interferometer are kilometers long. You bounce lasers hundreds of times back and forth along those arms, and what you're seeking to try to detect is a change in the shape of space-time as a gravitational wave passes by. A little bit like how an ocean buoy will bob up and down as an ocean wave passes by. And you do this using lasers. You have a network of these detectors around the world. We've got 2 in the US, there's 1 in Germany, 1 in Italy. And these are called LIGO, the US ones. There's Virgo as well. There's a Japanese one called Tamo. In fact, it's just undergoing a change of name. It's now called Kagra. And the goal here is to have a network of detectors so that as a gravitational wave passes by, we can detect it. Again, one of my jobs is to focus particularly on how gravitational wave observations might complement what we already learn about the universe from electromagnetic waves, from ordinary light, all the way from radio waves to X-rays. So again, see, that's a whole other topic in itself, but gravitational waves are founded on this idea that space-time can wobble, space-time can bend. So isn't that what you'd need if you wanted to make a jump into hyperspace? Well, you know, gravitational waves tell us something. If the next few years go as we hope, will tell us something about changes in the curvature of space and time caused by these violent events. We are trying to detect gravitational waves way up at high frequencies. There's plans on the table to launch a space mission to try to detect them from space as well, although we got a little bit of a setback this week because the European Space Agency, which has been the driving force behind that mission, I should say this slide is hopelessly out of date now because we hoped it might even launch in 2010. Clearly that didn't happen. It now begins to look, since the next big mission selected this week was an X-ray one for launch in about 2028, it begins to look as if that the space-borne gravitational wave mission might not happen until about 2034, thereabouts. So, you know, they'll even have made Star Wars Episode 9 by that time at the current rate. So again, it just emphasises that the time scale to do the real science can often be a time scale even longer than Hollywood these big blockbuster movies. So, as I said, that's my main idea for how you might plausibly, albeit implausibly, let's face it, but if there's any grain of truth in the idea of hyperspace travel, it's got to be something to do with our ability to warp space-time. So what kind of things would warp space-time? Well, that's where it gets a bit trickier, because it's really hard to imagine anything that could warp space-time that you could just conveniently carry on board a spacecraft like the Millennium Falcon. The kinds of things that warp space-time are things like this, a black hole. This is an artist's impression of an object that was discovered around the time that Star Wars first came out in the cinema. It's called Cygnus X1, and we think it's a black hole weighing a few times the mass of the Sun, which is orbiting around a massive blue star, a blue supergiant, and it's dragging material off. Its gravity field is so strong, it's dragging material from the blue star, and as that material falls down into the gravity well of the black hole, it releases a lot of energy, which we see in the form of X-rays, which is how we detected this object. So, carrying around a black hole on board your spaceship doesn't sound particularly practical, and yet frankly that's really what you'd have to do if you wanted to bend space-time enough to get anywhere near a plausible way to do hyperspace travel. There are plenty of black holes around. In fact, we pretty much think that most galaxies have got a black hole at their centre, and we can see the effects of black holes distorting the gravity field very vividly in a wonderful movie that's been made of the black hole around the centre of our galaxy. There's an X-ray source called Sagittarius A. You see here, this is a satellite called Chandra that has been up there since the late 90s. And this chap, Reinhard Getzel, No, I always got that wrong around. Gerard Renzo, he has been observing with these 4 giant telescopes in Chile, stars close to the centre of our galaxy. And here is a little movie, sorry, it's a wee bit blurry, it's not terribly high resolution, but you can maybe make out it says black hole there. So of course you can't see the black hole, but we can deduce from the orbits of the stars that that's where it is. And again, what I want you to notice is how fast the star speeds up. I mean, this isn't in real time, it's over many years, but it goes much, much faster when it's close to the black hole. So working out from the orbits of the stars how much mass there is concentrated in the centre, we've really been forced to conclude that if it ain't a black hole, it's something even weirder. So we think that black hole has got mass of more than 1 million times that of our sun at the centre of our galaxy, and we think that most galaxies have a similar supermassive black hole at their centre. Again, that's not really going to help us if you want to travel in your spaceship from one part of the universe to another through hyperspace. What you really want to do is to have a sort of pocket-sized black hole that you can switch on and off, and we don't know how to do that with gravity. Black holes bend space-time, they bend it so much that even light can't escape, but what you really want is a kind of a two-way system where you pop in one end and you pop out the other. So some of the more exotic theories of gravity, which are even beyond what Einstein studied, what we call quantum gravity, maybe give us some hints as to how you might do that. The idea of wormholes in space-time. The trouble is, however, wormholes are almost unimaginably small. They're so small that even a proton would be huge compared with the size of a wormhole. So how on earth are you going to fit a spaceship through one of those? Well, again, the real universe maybe offers some hints, which just emphasises my point that, if anything, our universe is even weirder than what sci-fi has dreamed up. Because in the last 15 years, we've come to see that something very strange is going on in our universe. It seems that the expansion of the universe that Edwin Hubble first established nearly 100 years ago, after whom the Space Telescope is named, the same guy, that expansion isn't slowing down, it's actually speeding up. Now, to think about what might be going on there, we can think of what would happen if I toss a coin in the air. If I throw the coin up with a certain speed, it goes so high and then it stops, but it's slowing down all the time, and then it falls again. And if I throw it a wee bit faster to begin with, it can go a bit higher before it stops, but it still falls again. Our universe, we thought, ought to be doing something roughly along those lines. The equations aren't so different, that basically the expansion that Hubble first detected, we figured from the 20s through to the late 90s that it ought to be slowing down just like the coin slows down, because all the matter in the universe is trying to pull it back together, just like the mass of the Earth is trying to pull the coin back down. Effectively, what we discovered in the late 90s is that actually what's going on is a bit like me throwing the coin up, and the higher the coin goes, the faster it climbs, and it doesn't come back down again. That would be weird, but that's what the universe seems to be doing. Now, what's causing that accelerated expansion? We don't really know. We have some ideas. It might be to do with the vacuum energy of empty space and the weird rules of quantum physics that seem to operate on these incredibly small scales. But there's some significant theoretical problems with those ideas, and really as an astronomer, I think all I can do is trust the data. The data do seem to be telling us that the universe is speeding up, but I wouldn't be so bold as to suggest that we really know why. And we've come up with a good name. We call it dark energy, but I've rather skipped over another topic, which is dark matter, which at least we've had a few more decades to get accustomed to that concept, because the first hints that the universe contained a lot of dark matter really began, well, some might say as long ago as the 30s, but certainly in the 70s and onwards. But dark energy is a more up-to-date concept and an even weirder one. Dark matter, we don't really know what the dark matter is, but at least it attracts other matter just like the Earth does and the Moon does. Dark energy seems to repel other matter. It seems to push the universe apart. And the name dark energy, I am reliably informed by some people that seem to know these things, was sort of coined first by a chap called Michael Turner, who is a very eminent astrophysicist in Fermilab in the US, in about 1999, which coincidentally is when Star Wars Episode 1, The Phantom Menace, came out. So it almost seems to itself be a homage to Star Wars. Now, rest assured, that's about the only time I'm going to mention the Phantom Menace tonight. But I still felt, for the historical record, that I should properly attribute the name Dark Energy to a kind of vaguely Star Wars origin. I'm sure you'll agree it really does sound as if it's something that belongs in the sphere of Darth Vader rather than in cosmology, but that seems to be what our universe is doing. And many of you will know, I'm sure, that this won the Nobel Prize for Brian Schmidt, Saul Perlmutter and Adam Rees in 2011. But again, they won the Nobel Prize for detecting this accelerated expansion, not for explaining it. We still don't really have a proper explanation. So time marches on. I should not spend too much longer on hyperspatial travel. I dare say I probably haven't convinced you that it's just around the corner and that you can book your tickets the way that people are booking their tickets for Virgin Galactic. But there are other topics I'd like to say a little bit about before we wrap up. So I'm going to move on now to a little bit about anti-gravity. Because again, this notion of dark energy, of space somehow being pushed apart by dark energy, well, if we could find a way to do that, it would be mighty useful, because it would effectively allow you to switch gravity on and off. And that is something that in the Star Wars universe people seem to be able to do quite routinely. And we certainly don't know how to do that in our universe. Gravity is always an attractive force. You feel weight when you're accelerated, and if you accelerate at a very great speed, then there's really not a lot you can do to somehow switch off that sensation of weight. So in particular, if you take something like the pod race, oh darn it, I've mentioned episode 1 again. Oh well, I'm sure you'll forgive me. Perhaps one of the better scenes in Star Wars episode 1 was the pod race, where Anakin accelerates from 0 to 600 miles per hour in about 2 seconds. It's amazing what you can find on the internet. Page after page giving you the top speed of Anakin's pod racer and all the kind of technical specs. So if you do the sums, that comes out to be a G-force, as we call it, of about 13 G. Now I know he's strong with the force, but I can't really see how he could have survived such strong G-forces without being squashed. And indeed, if you contrast that with, say, what typical fighter pilots would endure, they're momentarily having to experience maybe 4 or 5 G, but they would black out as much more. So I guess what's going on is that somehow, magically you might say, that gravity is being controlled in the Star Wars universe, that you can sort of switch it on and off. And there's numerous such examples. You see these sort of hovering platforms in the Senate building in Coruscant. You see Obi-Wan Kenobi being suspended in episode 2. You see the land speeder in episode 2, again just kind of hovering there. You see Plague Lars is, well, I nearly said wheelchair, but the point is it doesn't have any wheels. It just again sort of floats along. So you see routinely gravity just being controlled and switched on and off at will. Again, we just don't know how to do that. More examples, there's the land speeder from episode 4, there's a Cloud City from episode 5, which is of course my favourite one, The Empire Strikes Back. So if you look across the Star Wars universe, you see worlds of a range of sizes. In our universe, they would all have different gravities, because their masses are different, their sizes are different. The gravity on the moon is only about 1/6 that of the Earth. The gravity on Mars is about 1/3 that of the Earth. In the Star Wars universe, well, again, we don't really know how big the planets are, but if you take Tatooine to be roughly the same size as the Earth, then I guess it's reasonable that Tatooine would have a similar gravity to the Earth. But there are clear anomalies. For example, there's this little moon here. Well, as Obi-Wan Kenobi said, that's no moon, that's a space station. It's the Death Star. And this is a rather curious thing, which some of you might be aware of. Star Wars, as I said, shown in the UK in 1978, shown in the US in 1977. 1980, Voyager makes its way to Saturn and beams back images of the moon minus. What's going on there? However, the one thing I'm fairly sure of, although I still don't really see how they could have guessed what Mimas would look like, is that Mimas doesn't have the capability of blowing up planets, and moreover, it has a surface gravity that would be very, very much weaker than that of the Earth or indeed Tatooine. Because Mimas is basically just a dirty snowball. It's a few hundred kilometers in diameter. And if the thing that hit Mimas had been just a little bigger than what produced that crater, then Mimas probably would have been blown apart. So its surface gravity is really small, while in the Death Star, the surface gravity, and indeed the gravity it would seem all the way through the Death Star, is uniform and roughly what you find on Earth, because you see all these stormtroopers walking about, running about, hitting their head off, and things like that. So, we conclude that we can control gravity rather well. And again, I've probably said enough of the gravity, so now it's maybe time to move on to spaceships and weapons